With this module, we are starting a new topic of chemical thermodynamics, focusing on phase equilibria, phase transitions, and phase diagrams of pure substances. When we talk about phase equilibria of pure substances, we essentially explore the balance between different states or phases of the same substance. Imagine ice melting into water or water evaporating into steam. These are instances of phase transitions without a change in the chemical composition of the substance. There are numerous processes that can be classified as phase transitions, such as melting, sublimation, vaporization, and the transformation of one crystallographic structure of a substance in the solid state into another one, among others. But why and how do these transitions occur? What is fascinating is that these transitions are guided by a simple principle. At a constant temperature and pressure, any system will naturally evolve towards a state where its Gibbs energy is at its lowest. Note that our focus will be on thermodynamic phase transitions, which are reversible. In these transitions, the total Gibbs energy of the system remains constant. For any given pressure and temperature, the thermodynamically stable phase is the one with the lowest chemical potential. This insight is rooted in our understanding of chemical potential and reflects the system's natural tendency to minimize its Gibbs energy. It follows that when two or more phases coexist in equilibrium, the chemical potential of the substance is the same not only across all phases present in the system, but also within any particular phase. If there is any deviation, then there exists a possibility to reduce the system's Gibbs energy by redistributing matter within the system. For example, imagine that a certain substance is present both as a liquid and as a gas. At equilibrium, the chemical potential of this substance is the same everywhere, both between the two phases and within each phase individually. Now, let's investigate the mathematical representation of phase equilibrium at constant pressure and temperature. First, consider the chemical potential, represented by mu, of a substance in phase alpha. In this notation, the phase where the substance is located is denoted by a superscript. At equilibrium, this potential is equal to the chemical potential of the same substance in phase beta. For a pure substance, the chemical potential corresponds to the molar Gibbs energy, which is the difference between molar enthalpy and the product of temperature and molar entropy. This holds true for both phases, given that we consider equilibrium at constant pressure and temperature. Rearranging this expression, we find that during a reversible phase transition, the change in molar entropy between two phases equals the change in molar enthalpy divided by the transition temperature.